explosion erupted at about 4:47, ripping the store apart, blowing out the front and portions of the roof, demolishing the inside, trapping countless shoppers and employees, blowing out windows in nearby businesses in a roar that was heard miles away, leaving officials bewildered about the source of the gas.
The blast forced the immediate closing of over 100 small shops for nearly a week. In the weeks that followed, thousands of daily customers were kept away by the potential of more explosions and the closure of a number of streets in the immediate area.
That Ross store sits opposite the farmer's market and is flanked by a strip of retail stores, including the Kmart, which firefighters fear still poses the threat of explosion. As a result of that danger, more than 20 to 30 stores were evacuated. Flares have been placed in the streets to redirect traffic around that 4-block zone.
This is where the red tar pits are located, right here. This is Television City, and this is where the explosion took place at Ross Closed for Less. This is a little map showing the area. This is 3rd Street. This is La Brea. And every one of these black dots in the area indicates an abandoned oil well.
This rig is really not out of place here at all. Once the LA Basin was a forest of them, the largest urban oil field in the world.
Everyone knows by now what caused Sunday's devastating explosion and fire. It was natural gas, normally held underground by a thick layer of clay. Somehow, though, it seeped to the surface, where the gas collected in building basements until a spark set it off.
So, I think it does a message that, what Jim said to start off, it can be a real problem. The downside to having showed you that first is, like I said, it seems to be too dramatic. Because hopefully we're not going to have these situations as we deal with it. But what you're going to see going through the talk is that the regulatory agencies are in tune to this. In Los Angeles in particular, if you look at the groundwater goals of methane and groundwater, their numbers are very low. They're looking at about 1 ppm of groundwater on our industry. This is now being applied to people doing remedial actions, ERD and ISCR. So it's out there. It's out there because those kinds of situations happen and regulators are trying to do their job, prevent that from happening in the future. This is one of the CEU credit talks, and so some of these slides are not slides that I would give you, but I have to do it in a certain format, which I thought was a great idea, by the way. I'm surprised not more people did this, but I have to give you some disclaimers. One, these technologies, we represent them. And at the end, if you're taking the CEU course, these are the questions you should be able to answer by the end of the talk. And you're supposed to tell me, yeah, you did a good job, you presented these. And then you get your form, you get your CEU credits. So thank you for doing that. Okay, so what's Prevactis all about? I used to work for Ventus about 10, 12 years ago. And during that time, I worked on EHC and ISCR type technologies, which was combining carbon with zero venom iron. And those technologies worked really well. They were productive, they were useful, but there was room for improvement in that. And that whole company transitioned over, and I was aware of these patents that were out there, they were available to bring in. And there's a couple of them in particular that I was interested in. One is the use of alternative carbon sources. If you heard in the morning sessions, you heard people talk about carbon's not carbon. You need other things, anaerobes need other things. So there were unique carbon sources that had value, but really there was one guy right here, a way of inhibiting methane production during remedial actions, and a way to actively control and inhibit methane production. So that's what Prevactis ended up doing, is we brought these patents in, and we developed new types of technologies to do ERD and ISCR, let's say in the next generation way. So here's the presentation outline. I'm going to give you a real quick introduction on methanogens, what are they, what's the problem. Then we're going to talk about how do we control it, give you that's up here, and then some of the technologies that we provide to the industry. Okay, so it starts out pretty basic, but it gets a little bit more fun here. So what's methanogen? All right, it's an organism that makes methane, pretty straightforward. This is important to know. Back in like 97, Carlos, University of Illinois, he started all this RNA, DNA work that we've heard about lately, right? He used RNA gene probes and found that methanogens are very genetically distinct. They belong to their own domain. They're called archaea, right? And so from a genetic perspective, you and I are as different from dihalopicoides as methanogen is. So it's useful to keep that in mind, because if we're looking at controlling them specifically, genetically you can do that. Right? So certain antibiotics are not going to be active on certain organisms. You have to be targeting the right organism. genetic basis is there to do that. We also know that the pathogens are everywhere. They're arguably the most dominant organism in any environment, specifically in an environment that we're working with that's reducing. And then also from this morning's talks, if you heard them, we also know we don't want to kill them all. We need them. They're very important parts of synergistic microbial communities. Anaerobes work as communities, they live as communities. We can't just get one important member out and eliminate them. The whole system will fall. So that's the background. This is the one slide I really want to emphasize, not the fires from the beginning, but what's the problem with too much methane being generated? And this is the more frequent problem, and I think more important to us as practitioners in the industry, is that it represents a waste of amendment. We're spending X dollars for these products that we're buying. This is very straightforward math. It shows you on a Mueller basis, in this somewhat conservative scenario, 33% of the carbon we're adding, the hydrogen is going to methane if you make just 20 ppm methane in your water. And if you go back and look at some of the sites you have where you've collected methane data, you're going to see pretty much at least that. I've seen sites with hundreds of ppm, which is kind of hard to understand because solubility is about 28, but there's bubbles. They hiss, the pressurized wells bubble. Hundreds of ppm means it's probably 50% or more of the substrate that we bought and we spent the time injecting got wasted. It sent off as methane. So if we could control that, we save money immediately and become more effective in our remedial actions. And I emphasize this now in red and italics because, again, this is not the message we want to relay is that this is going to happen in all cases, but it's explosive. That gas you saw burning was a situation where there was too much methane, not from remedial action, but from a biological source. Projects that I've been involved with my career, using conventional ISCR reagents, not the reagents we're talking about today, we did have fires at one site in the Midwest. Twice. We injected our material, a couple weeks later, site's on fire, right? I wrote 2 papers saying, well, it wasn't me, but it wasn't on fire before. And it wasn't on fire a couple weeks later. This site, you could go to the state of North Carolina's website, and they're actively reporting on this every month. They used another conventional ISCR reagent in a backfill excavation at a dry cleaner site, and they generated up to 30% methane out of that hole. And the problem is that the building next door is a public church, and they've had explosive concentrations of methane in that church for about 8 months now. So what they've been doing is putting in an SVE system, and every month having to monitor that. So there's a couple more projects here, but I think the point is, if we can control it as consultants and practitioners, we don't want these projects on our desk. We don't want to be responsible for those kinds of sites. And so the regulatory community is on top of this. The state of Indiana has led the way. They actually have published guidelines, and they basically say, you're going to look at methane, excuse me, during remedial actions, and if you have above 10, you have to report. If you have above 28, you have to turn on an SVE system. So your remedial work plan has to have that contingency in place, and then if you hit that number, you've got to turn it on. There's 34 states that have indoor air monitoring requirements. A lot of these states now are putting methane into that monitoring program. So you're going to have to look at methane. So it's coming our way. I think it's coming our way, not because regulators want to harass us, but because they're concerned about the situation. Oh, at the very end, we're going to talk about how this works on metals too. So I've given this talk now since we started production about 7 or 8 months ago, and I think the biochemistry is the best part. But if you go talk to your larger clients about this, they zeroed in on the greenhouse gases. And so this is one summary that one client asked me to put together. And so if you look at this, you say he's got one site, and he's putting in 100,000 pounds of any substrate, you name it. We're going to say at least 30% goes up as methane. That's 30,000 pounds of methane. Well, you multiply that by 20 to get your CO2 equivalents. That's 600,000 pounds of CO2. He's got at least 10 projects a year doing that. By controlling the CO2 emissions, he can save tons of CO2 emissions, and that goes back to their sustainability index on their stock price. So they're looking at it as a financial driver. From our perspective, these numbers are arguable because you could say that, well, all this methane is really not going to go up into the atmosphere, but from their perspective, they want to take advantage of this. So you've got larger clients or people who are really tuned into sustainability indices. This is important to them. Okay, so now let's get at how do we control it, which I think is a really intriguing part of the presentation here. So what we have is the yeast called Monascus pervius. And you grow down a carbon source, typically rice, and you make this red biomaterial, biomass. In that biomass, these yeasts make 8 or 9 known statin compounds. Now, the one that you may know of is called Lipitor levastatin. They purified one, Merck, Pfizer, whatever, other companies, and they'll feed it to humans because it will control cholesterol biosynthesis in our bodies. But then you can buy red yeast rice off of the drugstore, and that's what it's doing. You're taking that because you're getting these statins to control cholesterol synthesis in our systems. You know, that's all well and good. You start thinking about it, you say, okay, well, why are these yeasts making something so complex so we can live healthier lives? They're probably not doing it for that reason, right? It's biological warfare on their scale. We know that bioactive materials are generated by lots of organisms to control their neighbors, right? So if you're a yeast in an aquifer system, and you want to compete for food in space, and the biggest bully in the room is the methanogens, and you can knock them down, you get a competitive advantage, right? So these are just examples of organisms making different bioactive agents, so it's well known that they do that. And so the yeasts are making these statins because methanogen uniquely contains pseudomurin in its cell wall structures, whereas Helichrysales contain peptidoglycan. These statins interfere with the biosynthesis of pseudomurin, specifically pseudomurin. So the methanogens can't grow into bio. You haven't killed them, but you've impeded their ability to grow, replicate, and develop, which is what you want. So this is just another picture of the same concept where we are not letting them grow their cell walls. So the other organisms are going to be able to take advantage of the nutrients and the space and the vitamins you've given them, occupy the niche, and then be able to better compete with the methanogens. There's another known mode of action that involves the F420 coenzyme system. And methanogens, again, uniquely drive the acetyl-CoA pathway. This is like the gas pedal for a system. There's a lot of carbon. They're going to slam on these systems, start making all these fatty acids, acetyl-CoA, but the methanogens are going to do that by a very highly regulated F420 coenzyme, whereas your acetogens are going to do that using NADH. So this is another known mechanism of how the statins could specifically interfere with the rate of proliferation of a methanogen. Okay, so that's probably half the talk, but I think it's important to know what we're doing, why we're doing it, how it works, when we start now looking at how we apply it in the field. So this was some of the earlier proof of concept work that was done by others, where there were 2 reactors going here, the green one and blue, an orange one and a blue one. So in the first reactor, they had 40 ppm, of the methane emitter, which we call Provide CH4, to the system. You can see at about 10 days, the methane production went from 60% headspace to about 0. Nothing was done to this reactor, so that was basically the control for the system. 10 days later, 20 milligrams to that reactor, see pretty much the same slope. In parallel studies, and we've done this now with SDC9 and KB1, related studies with KB1, not exactly these, but they didn't have a corresponding negative impact on D. helichrysales or D. helicobacter or whomever's out there, and they shouldn't have had, because everything we just talked about said these statins are not going to be negatively influencing those organisms. It's only going to negatively impact on the pathogen. The Navy's done some work with us in using tritium leucine uptake, and the way I'm using these data is they looked at 10, 25, 50, and 125 parts per million of the red yeast rice extract. And they showed at the lower concentrations, it actually has a beneficial effect on microbial growth and development. And if you think about that, I think it was Larry Wacket's talk, if he's still here, talked this morning about how things like vitamin B12 and chloronoids and other vitamins and minerals are very important to those, right? Well, that's what we're giving them. This is 99.5% yeast extract. There's 4% statins in there. So they're benefiting from the lower concentrations. The higher concentrations, it does seem to have a slower impact. So this helps guide our application rates. How much of this do we want to add to a targeted aquifer? hopefully you guys saw a cow really back on. If you didn't see a cow, you weren't paying attention. But there was a cow there with some bling on it to catch your attention. What's that all about? Well, if you go to the dairy science literature, you'll see that they've been feeding red yeast rice extract to cattle for a number of years to control rumen microbiology. They stopped the methane production in the rumens of these dairy animals or ruminants. First thing I thought is, okay, well, they're worried about the gas out the back, right? Well, they're not. They're more worried about gas out the front because it impacts their ability to chew, it impacts their teeth, not efficient feeders. But that industry has a lot of information on these organisms. There's no information you can find from that industry on dehalogenators or dehalochroides types of organisms because they really didn't care about that. So from a research perspective, you guys know there's a lot to be learned about how methane inhibitors impact these types of organisms. Okay, this is the last basic slide, but there's other methane inhibitors we're working on. Some from the dairy industry, some from others. From essential oils we're working on. We're always working on the next generation of these technologies. Because I think it's going to be very important to our industry, and I think we can make improvements as we go. Okay, so what are the products that we have for you as practitioners? One is just the methane inhibitor alone. It's a specially processed red yeast rice extract. It comes in these 55-pound drums. It's cold water soluble. You mix it up with water, and you put it on top of somebody else's carbon substrate that you put in the ground where you either don't want to make methane or they're making too much methane. Safe, easy to use. The emulsified products from what I see make the most methane. Emulsified whatever. Oils, alkanes, those kinds of things. I think it's because the cloudlets are so small, the pathogens really like it, and they make a lot of methane. So that can be one way to reduce the amount of material you need to add. And it also reduces the time you're spending on your injection contractor or your field contractor to apply it, right? Less material, less time. I got one case study to share some data with you on. It's a dry cleaner site from Georgia. Here's the former dry cleaner. Groundwater's going this way. Here's the strip mall. It's not a very high-class strip mall, right? Let's keep that in mind. This well, right outside that door, we added just ABC, which was a carbon substrate that a company called Redox Tax been using for a long time. In this well, cross gradient, we added ABC plus, targeted about 50 to 75 parts per million on the methane inhibitor. 6 weeks later, we went out there and here are the data. Groundwater data up top, you can see we reduced the amount of methane in groundwater from about 12 to 4, so 65% reduction. Not as significant reduction when we added just the ABC substrate. These data were lost, so the sample's lost doesn't mean zero. Now you look at the headspace of the well. If you ever go out to the site and you pop your well open, it was just pressurized, it hissed, it bubbled, it stunk, right? You've seen that? 35% methane coming out of that well. That was right outside that door of that active strip mall. And I was out there taking the data, and this is not high class. There was a trailer coming through, dragging his muffler, chains sparking, cigarette butts everywhere. That could be one of those other sites that we started off the talk with, right? So it is a real potential problem. We need to be more mindful of that as practitioners. Where we added the methane inhibitor, 0.5% methane coming out of the headspace. And but we took readings every 1 minute using these 2 meters, and we just stopped after 5 minutes. Okay, so using that data, we now have a product called ABCCH4, which is that carbon substrate with the methane inhibitor already integrated into it that you can buy in one drum, right? Because you want to be proactive. We want to be preventive in our remedial actions, not having to go out there and react or be curative in our application, because that's more complicated. Trying to kill and turn things off, it's much easier to prevent. So you can buy ABCCH4. Here is what it would cost you for this particular site. You go through the math, you can use anyone's calculator. This calculator that we use says, okay, I need 90,000 pounds of whatever amendment. I'm going to pay $1.50 a pound. That's just an average number. It says $135,000. I would have bought of amendment, if we did this 6 months ago. We don't need 90,000 pounds. We need at least 30% less. And I think that's a low number. 67,500 pounds, pounds of $1.50. It means I saved $33,000. There's a price of this now. It's $1.80, not $1.50, but $1.80 less, so it saves you $13,500 just in terms of shorter material cost. Doing it a better way, more effective way, I think a safer way. And it turns off or minimizes your need for putting an SVE system on when you exceed those numbers that the regulator is going to give you. So I think it's a pretty compelling thing. Nothing's perfect. I'm not saying this is perfect, but I think it's something we should be looking at. It's compelling. So now let's take one step down towards ISCR. I've been working on this for a long time, and I try to always differentiate ERD, enhanced reductive decoordination, from in situ chemical reduction, which was the synergistic effect of carbon and zero-valent metals, principally iron. But now the next generation, if you will, is anti-methanogenic ISCR, because a lot of the problems that we talked about is too much methane being produced using these reagents, right? So we have now anti-methanogenic ISCR reagents that we can sell. So the difference is these are not liquid substrates. These are now solid particles. We got solid zero-valent iron, solid carbon. We got to think about getting in those ground a different way. We have different reactions to take place, zero-valent iron reactions, ISCR reactions. And here's the problem that I've seen doing the ISCR projects. Look what we've created in the ISCR environment. Minus 375, minus 400 millivolt EH potential, near neutral pH. That's exactly where methanogen wants to be. They're going to double their cells every 1 hour, whereas the organisms you're trying to grow take much longer. So it's just a matter of a day or two, right, before they can't compete. You can keep pushing more carbon down there, but there's just no space for them. The methanogens have taken off. So if you can control them, just give the other organisms an opportunity to occupy those ecological niches, you then take advantage of all the things we talked about. If you read Paul's paper way back when, I asked him, hey, if you knew about this when you wrote this, would you kind of put this in a different category? He said, yeah, I would. He didn't agree with the space. And we're not saying the space has any significance. It's different. It's not any better. It's not any worse. It's a different way to think about ISCR reactions. So this is the ISCR product we have. It's called Prevect IR. Carbon, zero-valent iron, minerals, nutrients, specially processed. We injected with the geoprobe. Some people in the room didn't like this, and we actually got letters from their lawyers, but I really don't care because it's a factual slide. But what I did do as a modification to it is highlighted in yellow things that they apparently didn't read or didn't want to read. It's like, but there's multiple complex carbon doses. What does that mean? Well, we're not just giving them land-based plants, we're giving them kelps. Other marine-based organisms that have those coronoids and other proteins that anaerobes want, right? It's very important. It has the methane inhibitor in it. Integrated vitamins and nutrients. We're not just saying nutrients. Yes, there's nutrients and things. But integrated vitamins, nutrients, that are specifically selected to help anaerobes. Again, lots of talks we heard this morning on, well, what is it? B12, coronoids, other cofactors. A lot of other differentiators in there. And as a past consultant, I think these are useful slides. Okay, the last slide I have. I worked on a couple of heavy metal sites. Arsenic in particular was a problem because in theory, all these metals should precipitate out on an iron sulfide particle under a reducing environment. And in most cases they have. But if you've done ERD or ISCR and you've seen arsenic in particular increase, we always thought, well, it's a valence change, right? And I think it is partly valence change. But one client of ours allowed us to go back and speciate the arsenic that was increasing over time. And what we found is that, actually these are out of order, what we found is that all the arsenic that was showing up post-treatment wasn't the arsenite, it was methyl arsenate, right? It was this. And you go back to the literature, 1945, you find this pathway, let me go back, which showed that it's the methanogens again that love to methylate these metals. So if you can keep the methanogen activity down, at least initially, those heavy metals might have a better chance at precipitating and immobilizing. Now, it's not going to be 100% effective because other organisms besides methanogens will methylate metals. Clostridia will do it, other organisms will do it. But the big players are methanogens again. So that's what Prevect IRM is. It's a way to better immobilize heavy metals during ISCR reactions. So that's my summary slide. CEU guys, you should be able to answer the questions we gave you initially.